Hello and welcome to the 67th session of Porous Media Tea Time Talk. Here in the studio, I'm with Kiara, and we have two brilliant talks from Reza and Mahtab. We'll start with Mahtab. Mahtab earned her bachelor in mechanical engineering from University of Tehran, followed by a Master of Science degree in biomechanical engineering from Amirkabi University of Technology. She started her PhD under supervision of Dr. Zhao at McMaster University in 2019. And her PhD research has been focused on advancing experimental methods for studying multiphase flow in confined spaces. Currently, she is a postdoctoral fellow at McMaster University. The stage is yours, Mata.
Thank you. Hello, everyone. My name is Mahtab. Thank you for joining Porous Media Tea Time Talk today. I'm a postdoctoral fellow at the Chemical Engineering Department at McMaster University. I recently earned a PhD degree from McMaster University in civil engineering under the supervision of Professor Robin Zhao. Today, I present our recent research about beyond inhalation protection, assessing class mass effectiveness as source control devices. This work has been done under the supervision of Professor Zhao and in collaboration with Dr. Iranejad, Scott Laggard, and Professor Delanoy in chemical engineering, and also Professor Claes in medicine at McMaster University. My PhD focused on advancing multiphase flow in confined spaces using microfluidics. Then, as we all know, exactly 5 years ago today, on March 11, 2020, COVID-19, WHO officially declared COVID-19 pandemic. So I decided to work on this challenge as well during my PhD. I think the motivation for this research is pretty much same as why Porous Media Tea Time Talk webinars started in 2020. So when we talk about multiphase flow, we usually picture subsurface processes like geological carbon storage. But recent pandemic reminded us the importance of multiphase flow from human respiratory events. Violent respiratory events like coughs and sneeze generate numerous droplets with a continuum of sizes. The smaller droplets can remain airborne for a long time and propagate disease when they are inhaled by susceptible hosts. It is referred to airborne transmission. Airborne transmission was identified as the dominant transmission pathways of the recent COVID-19 pandemic. Wearing face mask is widely recommended as an effective measure to mitigate airborne transmission since they act as a barrier for droplet passage. Face masks reduce airborne transmission by providing two mechanisms, inhalation protection and source control. Inhalation protection means when masks filter out aerosol from inhaled air, while source control means when masks block the droplets that expel from infected person. Cloth masks play a critical role for public health due to their availability and reusability. Performance testing of masks for inhalation protection is well established. These methods involve maintaining steady-state airflow across the mask and also seeding the air with monodisperse submicron particles that mimic residue of pathogen-bearing droplet after evaporation. The mask performance evaluated based on two metrics: particle filtration efficiency, which is dependent on downstream particle and also upstream particle per volume of air, and also differential pressure, which is a drop in air pressure across the mask, which measures the mask breathability. Masks that have a high particle filtration efficiency and low differential pressure are desirable to wear. Existing testing standards are ill-suited to assess mask effectiveness for source control. These standard tests are performed under steady-state flow with relatively low flow rate, while violent respiratory events produce a high-speed jet tens of meters per second over a short duration, like less than a second. And also, droplets generated by violent respiratory events are not monodisperse. Instead, they have a wide size distribution that span orders of magnitude from submicron to millimeters. It's even more complicated than this, and large droplets produced during violent respiratory events are known to penetrate through mask and atomize into smaller dotted droplets due to their high momentum. Existing visualization techniques focus on tracking the plume generated by violent respiratory events, and these studies were limited by their inability to resolve individual droplets due to their relatively large field of view, and also quantitative measurements of the effectiveness of glass mask for source control is still lacking. Here we design a testing platform to evaluate the effectiveness of glass masks as source control devices. Our platform includes a mechanical cup simulator with a high-speed laser visualization system that allows us to precisely track the droplet passage through various glass mask fabrics. Visualizing aerosol in the out-of-plane direction, it means plane perpendicular to the flow, enable us to accurately measure the quantity and volume of individual droplet that escape through the mask. We use deionized water and nitrogen gas as fluid pairs since they are closely matched the surface tension of cuff droplets. Here you can see the image of the center that is established in 2020 at McMaster University called Center in Protective Equipment and Material. And this center established in response to breakdown in supply chains during COVID-19 pandemic. And here we designed a dedicated room for these laser visualization experiments to assess mask performance in real time. So we characterize 10 different woven cloth mask fabrics, and we label fabrics based on their materials like nylon, polyester, cotton, and we image it via bright field microscopy. We measure porosity, which is given by the areal ratio between pore space and bulk via image analysis. And then using the experimental setup, we track the droplet that escape through the mask as source control during a simulative cuff event. Here at the left video, you can see the escape droplets detection via laser visualization. The new droplets that emerge in each sequence are colored in red, and white ones are the droplets that remain from the previous frames. So we can count the droplet that escape through the mask, and also we can size the droplets and find the volume of the total volume of escape droplets that through the mask. And also we can measure the pressure drop across the mask fabrics for all the fabrics. So here you can see the results for 10 different fabrics, the volume of escape droplets, and we intuitively we expect that by increasing the porosity we would have a higher volume of escape droplets. But here is not the case, and we observe significant variation in source control performance, the volume of droplets VD among different fabrics, even with similar porosity. And we also measure the particle filtration efficiency of mask as an inhalation protection tool, following NIOSH standard using automatic filter tester specified for a standard test, and also charge neutralized sodium chloride aerosols that has a size of less than 0.1 micrometer. Here, we first find a significant variation in filtration efficiency for different fabrics for inhalation protection, similar to source control, which also does not correlate with porosity. And also, we found that the fabric effective for source control may perform relatively poor in inhalation protection. So the question is that what physical mechanism control mask performance when used for source control versus inhalation protection? For source control, during coughing events, droplet penetration through a given pore is possible if the kinetic energy overcomes viscous dissipation. And therefore, the ratio between kinetic energy and viscous dissipation must satisfy this dimensionless number, Reynolds times d over Tm. It should be greater than 1. Here, d is the pore size and Tm is the mass thickness. Additionally, droplet penetration through a given pore is possible when the dynamic pressure exceeds the capillary pressure, capillary interior pressure, which reflects in Weber number much greater than 1. And here, V is the droplet velocity, sigma is surface tension, and rho and mu is the liquid density and viscosity. Recent experimental studies shows that these two dimensionless parameters should be greater than 10 for a droplet to be able to pass through the pore. So here we define the pore to be active pore if it allows droplet penetration and when these two criteria are satisfied. So we defined a fabric material property called active porosity, which is defined as area of active pores to the total area of the mass. And plotting the total volume of these escape droplets as a function of fabric's active porosity collapses all the data onto single master curve, which demonstrates the fundamental control that active porosity exerts on mass performance for source control. For inhalation protection too, there are mechanisms that involve in inhalation protection like diffusion, impaction, gravitational settling, whose their importance depends on the particle size and velocity. For small particles, less than 0.1 micrometer, that is representative of aerosol residue and typical air velocity during breathing, similar to a standard test, the dominant filtration mechanism is diffusion and electrostatic attraction. Theoretical and experimental analyses have shown the filtration efficiency of single fiber in capturing charge neutralized particle due to diffusion is scaled as Peclet number to the power of -2/3. And also the filtration efficiency of homogeneous nonwoven fabric based on classical filtration theory is actually defined as this relation. So if we write down the Taylor expansion for this expression of a homogeneous nonwoven fabric, and we considered small alpha, which is alpha is the fiber packing density, we find that the filtration efficiency of homogeneous nonwoven fabric is scaled as eta times alpha times Tm over df. Here df is the fiber diameter, Tm is the fabric thickness, alpha is fiber packing density, it's the characteristic of the material, and eta is the filtration efficiency due to diffusion. So assuming the charge neutralized particle can freely pass through the pore spaces, filtration efficiency of homogeneous woven fabric could scale as this scaling relation that depends on the porosity and other characteristic of the material. So plotting filtration efficiency as a function of this scaling term collapses the data for inhalation protection. Here, as you can see at the right image. Then using experimental setup, we study the impact of existing water content on mask performance and source control. As it's crucial because during prolonged use of mask could become wet because of repetitive cough events like coughing, respiratory events like breathing, and also high humidity. So here we examine the volume of escape droplets and pressure drop over consecutive cough events, and we observe that volume of escape droplet increases with cough sequences and reaching a maximum at 4 sequence and then declining to almost 0. And also pressure drop significantly increases after 5 sequences. Here as moisture initially imbibes into smaller pores due to higher capillary suction, airflow persists through larger pores with a minor pressure drop. However, as water fills larger pores, the decrease in permeability causes airflow to redirect between the gaps between cuff tube and the mask holder, leading to near zero volume of droplet in later cups. So, in summary, we developed an experimental platform to evaluate the efficiency of face mask for source control. We demonstrate mechanistic difference in mask performance between blocking particles for source control and inhalation protection. And also, we introduced the concept of active porosity as a parameter that controls the effectiveness of mask as source control for reducing droplet transmission. Our finding also showed the intercorrelation between mask moisture content and filtration performance indicates that prolonged use may result in diminished efficiency due to moisture accumulation on the mask. So for more details about this research, please refer to the paper published in Physics of Fluids via the QR code here. Thank you so much for your time, and I'm looking forward to your questions.
Thank you very much, Mahtab. Very interesting presentation. For the audience, as we have noted, if you have any question, you can type down and we will definitely ask. Okay, I think we received one question here. Thank you for the interesting presentation. I have a question about video drops. Can you please elaborate how you performed the image analysis?
Sure. Okay, here. Let's see. Oh, here. Actually, we develop code in MATLAB based on the existing PIV code that can track the droplets in frame sequences based on the proximity principle, based on the pixel intensities. So here we use that code to find the new droplets in each sequence. It was important because we don't want to overcount the same droplets in sequence of frames, and we wanted to just count the droplet that emerge in a new frame. So yeah, that's it.
Thank you very much. I personally had a question. Would you please elaborate a little bit more on the experimental setup that you had? Like, how does it work?
Sure. Let me go to here. Yes, here we have a cough simulator that can generate the droplets, cough droplets with the same velocity as human cough droplets and the size distribution of that. And there's an atomizer here that actually that produce a high jet of droplet that impact on the mask fabrics, and mask fabrics actually attach using mask holder on the end of the tube and on the end of the cough tube. And here we have a pressure sensor attached to the cough tube that can accurately measure the pressure in the system. And also about the visualization setup, we have a high power class 4 laser, and using plano concave cylindrical lens, we can create a laser sheet, and in the front of that, in the front of the mask, we have a camera, high-speed camera, 4,000 frames per second, that can capture the droplets that comes out of the mask and hit the laser sheet, and they bright when they hit the laser sheet. So we can capture that from this plane, and yeah, that's about the experimental set.
Thank you very much. Thank you. If Chiara doesn't have any question, maybe we can move to the next speaker.
I actually have a question, if you don't mind. I mean, you were mentioning some sort of theoretical relationships, which like relate the efficiency of the mask to some parameters and properties of the fabric itself, right? And if I got it right, you were mentioning that you're using like a homogeneous conceptualization of your mask. And you shown at the very beginning of your presentation some like textures of the different types of fabrics that you acquired through some observations, I guess. And I was wondering, can you like assume that all of these fabrics are homogeneous, or do you see that some of them as like, I don't know, some heterogeneous patterns of the fibers? Or, I mean, if you just can comment on that.
That's a very good question. And the point is that yes, in micro scale, they are they may not homogeneous, but in macro scale, because they are woven fabrics, not non-woven ones, we can consider it as a homogeneous for our analysis. But in micro scale, there of course the fabrics have very complicated structure, and we cannot say it's homogeneous. But for micro scale and for woven fabrics, we could consider homogeneous behavior.
Thanks.
Thank
And thank you again for the presentation. Very, very nice.
Thank you.
Okay, so I guess that we can move to our second speaker. So our second speaker today is Reza Haghani. Reza is currently a PhD from the Department of Geosciences at NTNU in Norway. And his research is focusing on multiphase flow in porous media. And specifically, he's working on developing new models relying on lattice-Boltzmann methods. So combining theoretical and numerical approaches, his research aims at bridging the gap between complex fluid dynamics theories and computational modeling. So with this, I will leave the floor to Reza. So please, go ahead.
And thank you for the introduction. Hello, everyone. I'm Reza Haghani, PhD student at the NTNU and a member of PoreLab. And the topic that I'm going to talk about is the special characterization of wetting in porous media using local lattice Boltzmann simulation. And this presentation is actually based on a published paper with the same title. If you are interested, you can take a look at that paper. First, I want to talk a little about the wettability. What is the problematic with the wettability characterization, and what are the available methods? Then I will talk about our developed method, and I will finish with some summary and future plan. And whenever we have multiphase flow and there is a solid surface, when this interface between these immiscible fluids come in contact with the solid surface, actually a contact angle is formed. And this contact angle plays an important role on the characteristic or on the behavior of this porous medium. And this porous medium can be found whether in the nature, like a hydrocarbon reservoir, or in the industry, like fuel cell. And what we do is that we define the wettability as the affinity of the surface in with the two or more fluids, and it is usually characterized with the contact angle. And this contact angle can be defined, and it is affected by mineral heterogeneity, roughness, aging, porous geometry, and different parameters. And it is very important to find this contact angle. Here there is an image. And there is a here, for example, we have a porous medium, and this ganglion actually are the trap all inside the domain of solid, and the other fluid, which is, for example, here black. And different methods are available to find this wettability. The first one is the experimental method, but the problem with the experimental is that we find just one contact angle for the whole sample. We cannot find this distribution or especially contact angle inside the medium. On the other hand, with the advance of the imaging technology like micro-CD imaging, we can see what is inside the porous medium, and based on the segmented image of these micro-CD images, different methods have been developed, which can be characterized as geometrical method, topological method, and machine learning, thermodynamic based method, and multiphase based method. I will talk briefly about each of these methods. Uh, in the geometrical method, what we do is that we have a segmented image, and we first try to find the contact and three-phase contact point. Three-phase contact points are the places that the three phases meet each other. And after finding this three-phase contact points, what we do is that we try to play to um, bond surfaces between the two fluids and between the fluid and the solid. By finding these surfaces and finding the contact, the normal vector to these surfaces, we can use the dot product and find the contact angle between these two surfaces, which is actually the contact angle that we are looking. And these different methods actually are different just in terms of finding this normal vector, and some methods like on Amiri, they do some smoothing procedure, while others use the segments and use the voxelized image to find the contact angle. And this is the first method, and which developed. After that, we have the topological method, which developed by Son, and it is based on the Gauss Walnut theorem, which relates the Euler characteristic to the geometry of a ganglion. Here we have the uh, chi, which is the Euler number, and we have the Gaussian curvature, and we have the geodesic curvature. We can relate this geodesic curvature to the contact angle, and after doing some mathematical operation, we can finally reach this equation. This equation, as you can see, for each ganglion, we can find one contact angle. Another one is machine learning. We can train an algorithm, and then we can use our train algorithm to find the contact angle for the real cross medium. Here we have uh, two simple training models with available analytical solution, and we use it to train our machine learning system, and then we use it to find the contact angle. It was developed by Rahman in 2023. And recently, a thermodynamic-based method is also developed. It is based on the first law of thermodynamics, which says that energy cannot be generated or be uh, dissipated. Be, and based on the first law of thermodynamics, we say that the energy uh, that we input in the system, will result in the change in the surface energy of the system. The surface energy is defined like this, which A is represent the surface between the liquid and the solid, uh, subscript gas and liquid, and S represent the solid. And if we use the Young equation and place it inside the S equation, and we can consider that the external energy is the uh, capillary pressure times the change in the volume of the liquid phase, then we can find this equation, which is the contact angle based on the thermodynamics. In this method, we need to times or to a snapshot of the macroscopic images to see the difference between to see the changes in the area and the so in the area and the saturation to find this contact angle. In contrast to the previous methods that we only need one snapshot of the uh, Porous. And what we did is that we take advantage of numerical simulation. We know that in order to simulate multiphase, we need initial condition and a boundary condition for the contact angle. So if we take the initial condition from the photosynthetic images and we find the best contact angle that the old numerical simulation gives us a morphology or a fine steady state of the multiphase system that has a very that is very close to the initial image, then we can consider that contact angle to be the contact angle of the angular. So we use the lattice Boltzmann simulation because it is very close. It is much better than the theoretical methods like volume of fluid in terms of that we have box image, and the structure of LVM is that we can run our simulation on this box because the structure of the lattice is a box slide. Then what we do is that we start with separating each ganglion from the domain, and then we start with different contact angle from, for example, 0 contact angle to 180, and the contact angle which minimizes these differences is considered to be the uh, contact angle of that ganglion. And this technique is actually applicable for the three-phase contact line. If I go back here, the technique that we use can find the contact angle behind the three-phase contact line. Then what we need is to use an extrapolation or interpolation to propagate the information to other boxes that are not on the three-phase contact line. Uh, The error function that we define is a function which compares the initial image from the microcity image with the steady state of the numerical simulation. We compare it voxel by voxel, and this is the error that we want to minimize it. By minimizing this error, we can find the contact angle. Here we have three images with the three different contact angles. Affinity is related to the contact angle with this equation. Here, for example, for the contact angle of 19 as an input in the numerical simulation, we get this structure for the trapped ganglion. For the contact angle of 0, and this is the best contact angle, which we see that there is a little difference between the initial or the macrocity image and the structure that or method one. Then this obtained contact angle is considered to be the contact angle for the boxes along the contact line, and we go to the next ganglion. This is the portfolio of this structure that we start with separating ganglion, and we run the simulation for different value of the contact angle, and then we find the error, and through the optimization loop we find the minimum differences between the initial and the final shape. Then we go to the next ganglion. We use the 30 different benchmarks and that are available in the paper, but here I have I will show three results which we use our method to find the distribution of the contact angle. Some assumptions need to be said. First of all, that this method is based on the segmented image, not the raw images. And then, like other methods, we need to do some cleaning of the data, and we remove, for example, ganglion or trap ganglion and with the smaller size of 10 voxels in order to reduce the noise in our contact angle distribution. And then it is we assume that the initial condition that we get from the microcity image is the steady state condition, and the contact angle that we use is just for the three-phase contact line, and we need to use interpolation to propagate the information to the other voxels. Here we have a real porous medium and with the microcity images. And in the upper part, we have the ganglion, which is the wrap. This ganglion or the hole, which is inside the environment of the solid phase, and the other phase, which is the wrap. And in the lower part, we have shown the surface epithelium or the contact angle distribution. We compare it with the geometrical model, and we see that our method is able to better capture the distribution of the contact angle, because for this quarter which is the Benheimer stone, and the fluids inside it are gas and water. We are sure that this sample is whatever. But if we use geometrical method, we see that the distribution is close to 60 in contrast to our method, which is closer to the water system. We use it for another two systems, Wolverine-Benheimer, altered and unaltered. And on alter, we assume that we suppose that it should be a mixed with stone, and for the altered, for the unaltered, it should be butter with, and for the altered one, it should be mixed with. And we compare it again with the geometrical analysis, and we see that the more method is better in capturing the distribution. And here, as you can see in the geometrical analysis, we have a wider distribution compared to this method, which is the LDM simulation. Overall, we have developed a method. And this method, we expect that to be less prone to the noise, because in contrast to the geometrical method that very prone to be affected with the noise. Our method is less affected by the noise, and it is possible to run in parallel because you can either use the numerical simulation in a parallel mode and do it on a single ganglion, or you can send different ganglion to different core to simulate it at the same time. And yes, for the future, what we expect to do is that so far we consider one contact here for the whole sample, for the whole for all of the contact lines. Uh, and for the future, what we want to do is that to assign different contact angles for different contact line, or maybe to assign different contact angle to each of the boxes which are on the contact line. And we want to add this workflow to the package that we use for numerical simulation. And that's all. And just want to thank my co-authors and my friends, which really helped me in developing this paper. Thank you. I would be happy to answer any questions.
Thank you, Reza. Thank you very much for your very, very nice presentation. And once again, I'm asking anybody who has a question and is connected through YouTube to just type them into the comment section, and then we will read them out loud. Do we have any question from the studio? Madi, do you have any question? Not of now. Maybe I can.
Yeah.
Okay. I can start with one of my own. Reza, you were mentioning the accuracy of your method that you tested against the expected values, right, of the contact angles, and that seemed pretty nice. But I was wondering if you can maybe discuss a little bit more about the maybe disadvantages of your method, especially in terms of the computational burden associated with it, which I guess can be quite substantial with respect to the methods that are already existing and established in the literature.
So can I go back to?
Yeah, sure.
Here, if we start with the geometric method, we see that in the geometric method we have to have a very clean image in order to find this, to apply the geometric method. Because in the geometric method, what we do is that we use the three-phase contact line after we consider voxel, and we look around that voxel, 2 or 3 voxels, and then we actually put a contact line tangent to that interface, and then the contact angle between these 2 contact lines determines the contact angle of that boxes. And here they have shown that here, for example, even or when we do the segmentation itself has a lot of error in uncertainty. It is not very clear that, for example, the parameter that we use in the segmentation, what are that parameters. So we might end up to have different, to assign different voxels to different fluids, and even one voxel can change the contact angle 10 or -10. So for the geometric methods, we need to have a clean data, and what they have done is that they usually validate the data using the test case, which is dropped residing on an inclined surface. For the in terms of the computation, I should say that we just compare with this method Haghani, and we found that our method is faster. And we wanted to compare with others, but unfortunately, some of the methods are not available. The code is not available, so it is not very clear to. We couldn't actually compare it, and they didn't say anything about the computational cost in their paper. So it is a little difficult, but something that we are sure is that LBM is very is one of the main advantage of LBM is that it can be similar. It can be run on a parallel machine. So with this technique, you can do, for example, different ganglion at the same time. Each ganglion is run on one core, or we can use the uh, solver, which is parallel, for one ganglion. And the speed is we are expected to be high compared to other methods, and the accuracy is with the available data that we have. We see that the accuracy is good, but we haven't compared with other methods. With the and actually in the paper we have a benchmark, two benchmarks, and we compare the data with those benchmarks, but I haven't included it in this presentation. Overall, I think we haven't reached a method yet that we can say that it is the best method to use. There are still a lot of research going to find the best method, but it is still each method has its own advantages, disadvantages, but our method, I'm sure that with comparing with the geometrical, it is faster. I couldn't compare it with other methods.
Okay, thank you. Thank you very much. We have a question from the online participants. And Ashkan is asking, well, first of all, he is thanking you for the interesting talk. And he's asking if it is possible to detect the mixed wettability of porous media around ganglia using your method.
Yes, of course, it is possible to use it because what I can do, yeah. Need to go back. Here, the input for the simulation for the here we have a simple case. For example, we put the oil droplet inside the brine environment on a flat surface, and the contact angle can be changed from zero, which is the, for example, totally wet surface, to 180, which is non-wet condition. It is possible, but as we go closer to the uh, totally wet or totally non-wet, when we are closer to, for example, less than 10 contact angle, when it is less than 10 degrees or more than 170 degrees, the accuracy is less than the other range. But it is possible because it is just an input parameter. So, and here you can see that we use the code for different contact angles from 60, 90, and 120, and it can be increased. And we did the simulation until 160 and started from 20 actually.
Okay, thank you very much, Reza, for your presentation. Also, Ashkan is thanking you for your answer to his question. So if we don't have any other question, I think that we can close this session here today. And while closing this, let me just also advertise a little bit. So before closing, I just want to thank our two speakers today and all of the people who attended the seminar online. And of course, also Madi, who was leading the session today with me. So our next talk is scheduled for the 15th of April, and more details about that, about our next speakers, and about the timing will come through our social media in the near future. So I remind you that in case you're interested to presenting at one of these online events, you can just drop us an email at the email that you see here. So porosmediatt@gmail.com. Thank you again, and see you next time at the next session. Bye.